In this lecture, we will study the periodic refractive index modulation in the fiber core. These periodic structures are called grating. So, we are going to study fiber gratings. So, what we have is in a fiber, if we create periodic refractive index modulation, then these kind of structures can be used as components or devices in telecommunication and sensing systems. Depending upon the periodicity of this modulation, we can have short period gratings or long period gratings. Short period gratings are also referred to as fiber Bragg gratings, because the phenomenon is equivalent to Bragg reflection or Bragg diffraction in crystals. Typical refractive index modulation amplitude is 2 into 10 to the power minus 4, and length of the grating is few millimeters. It can be a couple of millimeters to 10 or 15 millimeter. So, let us understand how does it work. First, we will consider fiber Bragg gratings. So, we have this refractive index modulation. We have low refractive index, high refractive index, then low refractive index periodically. Now, when a light beam is incident here, because of this index contrast, a part of the beam gets reflected from this interface, part of the beam goes out, and then it gets reflected from the rear interface. Similarly, from all the other layers there would be reflections. What happens is that when all these reflections are added up in phase, then we can have a very strong reflection, and this will happen at a particular wavelength. So, in order to understand this, let us zoom this and consider different waves here. So, when this wave is incident here, this is the incident wave, and we have the periodicity lambda. So, for convenience, let us divide it into lambda by 2 for high refractive index region and lambda by 2 low refractive index region. Let us say in high refractive index region, the refractive index is n0 plus delta n0, and in this region it is n0 minus delta n0. Now, when this wave is incident here, a wave gets reflected from this interface, let us say it is A. A part of the wave gets reflected from this interface, let us say it is B. Okay. Then whatever portion of the wave, whatever fraction of the intensity goes out here, that gets reflected from other interfaces. If all these three are added up in phase, if they have a phase shift of 2 pi or integral multiple of 2 pi, then we will have strong reflection. Let us find out the condition for this strong reflection and wavelength at which this will happen. So, if I consider these two waves A and B, then the phase difference between A and B would be pi minus 2 pi over lambda naught times n0 plus delta n0 times lambda, because this is the path difference from here to here. So, lambda by 2 and lambda by 2 in the refractive index region of n0 plus delta n0. So, this is the path difference, and this pi phase shift occurs because there is a reflection from rarer to denser interface media. So, I have delta phi AB, the phase difference between these two waves. Similarly, I can have delta phi BC, the phase difference between these two waves, and if all the three waves have to have constructive interference, and let us say this happens at wavelength lambda b, then if I take the total phase shift, the phase shift between these and these, there it should be integral multiple of 2 pi, and for m is equal to 1, if I take the value of that integer as 1, then it should be equal to 2 pi, and if I put the expressions from here, the lambda, the value of lambda b will come out to be 2 n0 times capital lambda, where I have assumed that delta n0 is much smaller than n0, and which is the case because n0 is typically 1.5 and delta n0 is about 2 into 10 to the power minus 4. So, I can neglect n0 with respect to I can neglect delta n0 with respect to n0. I can also understand this interaction as coupling between two modes. If I have a fiber, let us say I have a single mode fiber. So, in a single mode fiber, if I launch light from this side, the mode is excited and mode propagates in this direction. If this is ideal fiber and there are no scattering centers, and if I have index matching liquid at this output end, then there is no way that the light will travel back, okay, because there is no back reflection from here, there are no scattering centers. So, there is no mechanism by which the wave can travel back. So, in general, even if I do not put index matching liquid here and there are some scattering centers, then the light which comes back is very small. So, most of the light goes in forward propagating mode. This grating here acts as periodic refractive index perturbation, and this perturbation can couple light from forward propagating mode to backward propagating mode. So, if I have forward propagating mode whose propagation constant is beta plus and backward propagating mode whose propagation constant is beta minus, and of course, since it is single mode fiber, so these modes are the same, their propagation constants magnitude are the same, only their directions are different. So, this magnitude beta plus would be equal to magnitude beta minus, let us say it is equal to beta, and if n effective is the effective index, then I can write it down as 2 pi over lambda naught times n effective. If the wave vector corresponding to this periodic refractive index modulation or the spatial frequency is k is equal to capital K is equal to 2 pi over capital lambda, then if this k is such that this length is equal to this, then if a mode goes like this and then capital K takes it here, so the resultant would be beta minus. So, in this way I can couple power from beta plus to beta minus, and the condition for this mathematically can be given by twice of this magnitude, that is 2 times 2 pi over lambda b times n effective, it should be equal to the magnitude of this k, which is 2 pi over capital lambda. So, this gives me lambda b is equal to 2 times n effective times capital lambda. So, this particular wavelength will satisfy this condition, and all the power in this spectral component can be reflected back. Typically, if I take a silica glass fiber, n effective is of the order of 1.5, typical value 1.5, and if I consider the Bragg wavelength as 1.5 micrometer, so this periodicity required is about 0.5 micrometer. So, these are sub-micron gratings, so this periodicity is really very small. That is why these Bragg gratings are also known as short period gratings. We can study the power evolution in the forward and backward propagating modes by using coupled mode theory, and in coupled mode theory the amplitude of the forward propagating mode varies with z according to dA over dz is equal to kappa b e to the power I gamma z, and that of backward propagating mode varies as dB over dz is equal to kappa a e to the power minus I capital gamma z, where capital gamma is 2 beta minus k, which is nothing but phase mismatch. If gamma is equal to 0, then there is phase matching between the forward propagating mode and backward propagating mode. Intuitively I can say that it is clear that for efficient coupling between the forward propagating mode and backward propagating modes, you should have phase matching conditions satisfied. So, gamma should be equal to 0. If I look at these two equations, the equation of A contains B and equation of B contains A. So, these are coupled equations, and this theory is known as coupled mode theory. Now, this coupling between the two modes occurs due to periodic refractive index modulation, and in the grating region, if I write down the refractive index, then I can write it down as delta n g square. G refers to grating. X y z is equal to n square of x y plus delta n 0 square sin k z, where I have considered this periodic refractive index modulation as sinusoidal. So, this is a sinusoidal refractive index modulation with with a spatial frequency k or wave vector k. So, if I use this, then I can show that this kappa which is known as coupling coefficient is given by omega epsilon naught by 8 integral over x and integral over y psi star del n square x y psi dx dy, where psi is normalized modal field, it is power normalized modal field. Now, if I consider a single mode fiber and consider Gaussian approximation, that is, I approximate my mode of the single mode fiber by a Gaussian of width w, then this integral can be written as I is equal to 1 minus exponential minus 2a square over w square, and then this kappa can be represented in terms of this integral as pi delta n 0 times I over lambda b, where a is the core radius and w is the Gaussian spot size of the mode. So, in order to find out kappa, I need to find out overlap integral, which is this, and you can see that it depends only on fiber parameters. What is the mode spot size, Gaussian spot size, and what is the core radius? It involves minus a square over w square, and I know that for a given fiber w over a varies with v like this. This is the empirical formula given by Marcuse. So, I can now find out how this overlap integral will vary with v. It is very simple now to do this. So, I can see that as v increases, this overlap integral increases. Typically, around between 2 and 2.4, the value of this integral is around 70% to 80%. Okay. So, there is almost 78% to 80% overlap between the modes via this short period grating or fiber Bragg grating. So, this is, with the help of this, I can find out what is the strength of interaction. So, the strength of interaction, which is defined by coupling coefficient and given by pi delta n 0 I over lambda b. Now, I already know how I varies with v, then I can find out how kappa varies with v. If I take typical value of delta n 0 as 2 into 10 to the power minus 4 and Bragg wavelength as 1550 nanometers, then kappa varies with v like this. Again, I can see that typical value of kappa for the values of v from 2 to 2.4 is about 0.3 millimeter inverse. So, it is around 0.3 millimeter inverse. If you go to shorter values of V, then it can be around 0.2. Now, with the help of this, since I know how A, which is the amplitude of forward propagating mode, and B, which is the amplitude of backward propagating mode. So, the equations describing the variations of A and B with Z I already know. So, if I solve these equations for given kappa, for given fiber, for given grating, then I can find out how much would be the reflectivity, because from these amplitudes I can find out the powers, and if I find out the ratio between the reflected power at the input end of the fiber and the incident power at the input end of the fiber, then I can know what is the reflectivity. If I work that out, then reflectivity comes out to be kappa square sine hyperbolic square gamma z divided by gamma square cosine hyperbolic square gamma L plus capital gamma square by 4 sine hyperbolic square gamma L, where gamma square is small gamma square is kappa square minus capital gamma square by 4, and this expression has been obtained using the conditions that at the input end of the fiber, that is at Z is equal to 0, A is equal to 1, that is all the power is in forward propagating mode, and B at Z is equal to L is 0. Okay. So, when light reaches to the end of the grating, then at that value of Z the power in reflected mode or the backward mode is 0, okay, which means that all the power gets reflected. At Bragg wavelength lambda b, phase matching condition is satisfied. So, 2 beta is equal to kappa, which means capital gamma is equal to 0. If capital gamma is equal to 0, then a small gamma is equal to kappa. If I use this in this expression, then the reflectivity of the grating comes out to be 10 hyperbolic square kappa L. If I plot this reflectivity as a function of kappa L, then what I see that as I increase kappa L, the reflectivity of the grating increases, and eventually for large values of kappa L it will eventually reach the value unity, there would be 100% reflection, but that will occur at the value of kappa L is equal to infinity. But what I can have is that at kappa L is equal to 3, if I work this out here, read this out, then at kappa L is equal to 3, reflectivity is almost 99%. So, this value of kappa L is sufficient for me. This happens when I am at Bragg wavelength. So, if I choose, let us say kappa L is equal to 3, then at Bragg wavelength the reflectivity is 99%. Now, if I slightly move away from Bragg wavelength on either side, then phase matching condition is not satisfied and the reflectivity will drop down. So, what I anticipate that at lambda is equal to lambda b, there should be a peak in the reflection spectrum, and as I move away from this lambda b, the reflectivity would fall down. Here I show how the power in the transmitted and reflected modes vary as a function of z. What is the evolution of power in the forward and backward propagating modes for different values of kappa. For a given grating length L is equal to, let us say, 5 millimeters. I can see that when kappa is a small value, say 0.1 millimeter inverse, then even at L is equal to 5, I have the transmitted power drops down only by 20% and it will almost saturate, and the reflected power is maximum, it is around 20%. It will take very long length for this power to go beyond this. However, if I increase kappa, then I can increase this power, the transmitted power drops down and the power in reflection mode increases, and when I have the value of kappa around 0.4, then I can see that the power in reflected mode is, or backward propagating mode is, more than 90%. And if I have the combination of kappa and L is equal to 3, then of course the reflected power would be 99%. Here kappa times L is only 2, 0.4 times 5. Let us find out what is the optimum grating length if I want to have reflectivity, let us say 99%. I can always find out the grating length required for a desired value of reflectivity, because I know that the reflectivity varies at 10 hyperbolic square kappa L. So, L would be 10 hyperbolic inverse square root of R over kappa. This plot is for delta n is 0 is equal to 2 into 10 to the power minus 4, lambda b is equal to 1550 nanometers, and for the value of R 0.99. So, in order to have 99% reflection. So, if I vary my fiber parameters, that is I vary the value of V, then this is how the length of the grating has to be tuned to achieve 99% reflectivity. I can see that if the value of V is large, then the grating length required is smaller, and for smaller values of V, I require much larger grating length. It is obvious, because if I increase the value of V, my mode is more and more confined in the core and the overlap integral increases. While if I go to shorter wavelength, then the field spreads out from the core and the overlap integral, minded that this overlap integral, since grating is only in the core region, so it is the power in the core region that matters. Okay. So, if power in the core region is small, then the overlap integral would be smaller, and hence you will require much longer grating to reflect back 99% power. Let us work out a few examples. If I have a typical fiber Bragg grating with delta n0 is equal to 2 into 10 to the power minus 4, and I assume 75% overlap between the forward and backward propagating modes via fiber Bragg grating, then let us calculate coupling coefficient at 1550 nanometer wavelength and the required grating length for 99% peak reflectivity at 1550 nanometer wavelength. I know the coupling coefficient is given by pi delta n0 times I over lambda b, and delta n0 is 2 into 10 to the power minus 4, I is 0.75 and lambda b is 1550 nanometer. So, this gives me the value of kappa about 0.3 millimeter inverse. What is the required grating length for 99% peak reflectivity? So, I know the reflectivity is given by 10 hyperbolic square kappa L. So, L would be tan hyperbolic inverse square root of r over kappa. R is 0.99 to have peak reflectivity 0.99%, and the value of kappa I have obtained at 1550 nanometer wavelength as 0.304. So, if I put these values here, I will get the grating length about 10 millimeters or 1 centimeter. Let us now look at reflection and transmission spectrum of the grating. If I incident this spectrum, which is broadband spectrum, then out of all these wavelengths, only one wavelength which satisfies the condition 2n effective capital lambda is equal to lambda b, that wavelength will be reflected and all the other wavelengths will pass through. So, in the transmitted spectrum, this wavelength lambda b would be missing, and in the reflection spectrum this wavelength will appear. Then what is the spectral width of this? The spectral width of this reflection spectrum is given by delta lambda is equal to lambda b square divided by n effective times L times 1 plus kappa square L square over pi square to the power half. So, if I know all these values, n effective, kappa L is given for given reflectivity, and then it will depend upon what is the value of n effective, what is the value of L. This is typical reflection spectrum. For delta n 0 is equal to 2 into 10 to the power minus 4, grating period about 0.54 micrometer, and L is equal to 11 millimeter for a typical single mode fiber. So, this grating period with for the given single mode fiber gives me lambda b is equal to 1550 nanometer. So, I get the peak reflectivity at 1550 nanometers, and look at the value of delta lambda. Delta lambda is about 0.2 nanometers. Delta lambda is the width at which the power falls down to 50% of its peak value. So, it is about this width. So, delta lambda here in reflection spectrum of fiber Bragg grating is really very small. It is 0.2 nanometer or even less, depending upon the length of the grating, depending upon other grating parameters and fiber parameters. If I look at the spectral width for a typical fiber given by N1 is equal to 1.447 and N2 is equal to 1.444, then if I change the value of V, then delta lambda changes according to this. For reflectivity 99%, I know for reflectivity 99% kappa L is equal to 3. So, all the value here in this bracket is fixed. Now, it will depend only on the grating length and N effective. N effective means the fiber, and the Bragg wavelength, which also depends upon fiber parameters. So, what I see that as I vary V, that is I change my fiber, then delta lambda varies between, let us say, 0.15 to 0.25 nanometers. It is in nanometers. Why do I obtain this kind of variation? How can I understand this kind of variation? If I increase V, then L decreases. This I have already seen, that if I increase V, the length required for 99% reflection decreases. If I increase V, N effective also decreases. So, if L decreases and N effective decreases, then delta lambda would increase. So, this is how I can understand this curve. In the next lecture, I will work out some more examples and look into some applications of fiber Bragg grating. Thank you.